This is a lesson on composition with radical functions in a course on precalculus. I had covered in a previous lesson composition of functions, actually several lessons. I started with just linear functions, but we've done this parabolas, we've done this with cubic functions, we've done this with rational functions. You should be able to be proficient at this skill. I wanted to remind you, however, do a quick review about operations with radicals. I had done a review about definitions of radicals, all right, and you can look back at the previous lesson about that. But when we're looking at product properties and adding and subtracting radicals, there's some rules that we need to remember. Okay, let's do the operations of adding and subtracting, and in here I have some simplification as well. Looking at this first example, I'm going to simplify 12x under the radical. Remember, 12x can be 4 times 3x, or you may even write it with its smallest prime factors. 4 is 2 squared, and then we have times a 3x in there. Plus 5, 27 is going to be written 9, which is 3 squared, times 3x. And so when I see those squareds under the radical, I'm going to bring that factor out. So I'm going to bring a factor 2 out. I get 4, the square root of 3x, plus 5 times 3, 15, the square root of 3x. And when I add those together, I get 19, the square root of 3x. Okay, so this should be a review for you. It should be a review for you to find prime factors. And it should be a review for you to use those prime factors in order to simplify a more complicated radical expression. I expect you to be proficient at this point. Let's do another quick review. I have higher powers of x under the radical. I wanted to talk about that. The square root of 4x to the 5th, let's rewrite this. This will be 2 squared times x squared times x squared times x. Are you okay if I say x to the 5th? 2 plus 2 plus 1 is 5, right? So I'm going to divide all those up. And this term is going to simplify down to 2x squared, the square root of x. All right, I can take this factor of x out, this factor of x out, this factor of 2 out. So I get 2x squared, and then this single x is still under the radical. I'm going to play the same game with this next term. I have 3 squared, x squared, x squared, x. So this is going to simplify to 3x squared, the square root of x. 2x squared, the square root of x, minus 3x squared, the square root of x is negative x squared, the square root of x, and that will be the answer for simplifying that. So when you're doing adding, subtracting, you want this very similarly to, like, if I have 4a plus 5b, I cannot add these together. That does not turn into like 9ab or something. Do not be making up your own rules. If these two terms in here are not the same, I can't add them. So that's why down here, I can't just add these two terms. I have to get this common term between them, and then that will allow me to add them. Okay, let's multiply. Let's do a multiplication example in here with radicals. It has a 4th x. Both of these are to the 4th root. So I'm going to take all of it and put it under the 1 radical. That's what I'm going to do, is just put it under 1 radical and then simplify from there. 8 is 2 cubed times 2. There's a 2 to the 1st power here, and then I have an x times an x cubed. You may notice right away that I have a 2 to the 4th x to the 4th, so this simplifies to the 4th root, and x to the 4th to the 4th root. I get just a 2x out of here. Those just factor. I don't have any radical. I don't have a radical left there. So that's a review for adding, subtracting, and multiplying radicals. I know that's a good refresher. I also wanted to refresh you about dividing by radicals. By mathematical convention, radicals are not allowed in the denominator. I don't know if you remember that, but they're not allowed. So this square root down here, even if it was just like the square root of 50, not allowed. You can't have any radicals in the denominator. So what we want to do is multiply the numerator and denominator by the conjugate. I'm going to talk more about the conjugate in the next slide, but I'm going to do this simpler example here for you, just to remind you how to do this stuff. The first thing I want to do is simplify whatever's under this radical here. I'm not going to go ahead and multiply by something large and crazy. If that simplifies, then I can do something simpler later. So I'm going to leave this 5 times x to the 8th power up top. I'm going to remember that 50 is 25 times 2. X to the 13th is x to the 12th times x to the 1st. And I have that under the square root. So this is going to simplify to 5. This is going to simplify to x to the 6th. And then I still end up with a 2x under the radical there. Do you see that? So then I'm going to have a 5x to the 6th, the square root of 2x. That's how that's going to simplify. Looks like more simplification goes on. I'm going to cancel that 5. I'm going to cancel the 6 and put a 2 up here. I'm going to get an x squared over the square root of 2x. So right away you can see that step here, in order to simplify, that's going to make my work easier, x squared. So let's get rid of that radical in the denominator. Now that it's a simpler denominator to work with, I'm going to multiply the top and bottom by that value. If I multiply by this value, if I multiply by itself, there's no radical anymore. All right, that's the trick. You just use it to get rid of its own radical. If I multiply by the bottom by root 2x, I need to multiply the top by root 2x. When I multiply root 2x times root 2x, I get a 2x in the denominator, and I'm left with the x squared root 2x up top. One more step here. It seems like that x cancels with that x. I'm going to write it out like this. 1/2 x, the square root of 2x. I think that's the most elegant way to write that solution there. Or, yeah, that expression. Okay. So, 2 tricks here that were a reminder. Make sure you simplify that denominator term before you do the getting rid of the radical in the denominator. And then this step here, make sure you're multiplying by a factor of 1 overall. So if you do it in the bottom, you have to do the same exact thing in the top. All right, so let's look at a conjugate example. I pulled up this conjugate example, rationalize the denominator and simplify completely. So if I want to get rid of this in the denominator, I multiply by its conjugate. And you may remember this with the complex numbers, the complex conjugate, where wherever I had an I term, its complex conjugate would be to put a plus sign in front of the I in the other term. We're going to play the same game here. A little bit different though, I guess, a little bit different, is we're going to take the opposite of whatever that sign is in here. So I'm going to take the square root of x plus the square root of 10. I'm going to remind you, when I take the square root of x minus the square root of 10 times the square root of x plus the square root of 10, I'm going to have the difference of squares. Do you see the difference of squares there? I'm going to have x squared, the square root of x squared minus the square root of 10 squared, and notice that gets rid of the radicals, x minus 10. All right, so when I multiply this through, I'm going to get x minus 10 down in the denominator. No more radicals anymore. But because I multiplied by this on the bottom, I still need to multiply by this on top. And so I'm still going to have radicals in the numerator here. I have to FOIL this, right? I have to FOIL all of these terms out. The first 2 terms, I get an x. The last 2 terms, I get a plus 10. The cross terms in the middle there, I'm going to get a plus 2 the square root of 10x, right? So I'm going to call that my solution. It's not the most elegant solution, but that is by convention simplifying so that there's no radicals in that denominator there. The last task I have for us today is to look at composite functions. We've been doing composite functions all along with an array of toolkit functions. You're not surprised to see that we're going to be doing it with radical functions. So when we look at radical functions, and I had mentioned this a little bit with the lesson with extraneous solutions, is we need to double check what's under that radical, and that will be limiting our domain. Okay, and it may be the case with one situation and not the other where I really need to get excited about the limited domain due to radicals. And so I have these two examples here in order to explore that. Okay, and you're not going to be surprised that I also looked at the graph of these. Remember, always with functions, if you're asked for a domain, you can look at that graph. It won't show you any holes, but it will show you the allowed and unallowed values. Okay, so let's look at this first part. The first part asks, part A, find f of g of x. So I'm going to take g of x and I'm going to put it in f. So wherever I see x in here, that's where I'm going to put g. So I'm going to get negative 2. G is the square root of negative x plus 7. I'm going to put a parenthesis around that and close that there just to remind you that the plus 5 goes outside the radical. It does not go inside the radical. The 7 is inside the radical, but then that's the end of x. That plus 5 cannot just go under that radical. And I'm going to tell you that is that composite function. You cannot simplify this anymore. That's it. When I look at the domain, I need to note that I have to, and we've covered this in prior lessons, I have to take the domain of the original inside function, and I have to take the domain of I have to check the domain of the resultant function. All right. So the original function does have limited values, right? Negative x plus 7 has to be greater than or equal to 0. I'm going to move the x over here. So you can see I get 7 is greater than or equal to x, but more importantly, I need to write it so that it says x is less than or equal to 7. All right, for any number less than 7, I'm going to get a positive value in there. All right, so that is true for the inner function, and while I'm looking at the resultant function, that's the same thing true as for the resultant function. So for this domain, I'm going to say that it can be any number from negative infinity all the way up until 7 and include 7. I can include 7 in there. So that's going to be the domain for this function. We can check out the graph real quick here. Let me bring the graph forward here. The graph looks like this. I have upward facing radical, and it's flipped about the y-axis as well. It's flipped about this axis, and it's flipped about this axis, and it's moved up 5. It's transformed a bunch here. And so you can see that here's the 7 value, right? Here's x equals 7, and it can equal any value less than that. So that's how I get this value. The domain is from negative infinity all the way up until that value 7, and it can include 7. Let's do g of f of x. Let's do part B here. G of f of x. I'm going to take wherever I see x and g, I'm going to put 7. So wherever I see x and g, here's x and g, I'm going to take this whole thing and put it in there. Okay, so that means I'm going to take the square root of the negative 2x plus 5, and then that plus 7 is still under the radical. Sometimes I like to put a little, like, I don't know, close off here so it's clear to me anything after this is outside the radical. That's why I put that little exaggerated end of the square root there so that you know explicitly that's where it ends. Let's simplify this. I think we need to distribute a negative here, and then we also have some constants that will add up. I'm going to get a plus 2x minus 5 plus 7, so that's a plus 2. So that's my g of f of x. When I look at the domain, I'm going to have to look at the domain of the original inside function, and I'm going to have to look at the domain of the outside resultant function. Not the outside function, but the resultant function. All right, so we'll look at the inside. When I look at a line, there's no restrictions on input values for a line. I'm okay with that. When I look at this here, when I look at the final function, I'm going to have to say 2x plus 2 is greater than or equal to 0. 2x is greater than or equal to negative 2, so x is greater than or equal to negative 1. So my domain is from negative 1 all the way up to infinity. It can't equal infinity. I'm going to put a square bracket on one end and then a parenthesis on the other. Let's bring up this graph. I know you want to see the graph here. We're always checking the graph with domain. I graphed that. That's why I graphed. I just put that function in there. You can see that's what it looks like. And here's our negative 1 value. It starts at negative 1 and goes all the way up to infinity. All right, so that's what I set for this domain, negative 1 up to infinity. So hopefully that clarifies for you a little bit when you're doing domains, how to find domains with radicals algebraically, and then having them verified with your graph.